Hello everyone, my name is Luke Vassallo, and in this video I will be presenting the paper which I co-authored with Dr. Josef Bayada for solving the PCB placement problem with reinforcement learning. A brief overview of the presentation. In the upcoming slides, I will start by providing a brief background to physical design and the context of printed circuit boards and motivation for automating this task. Next, I will present our methodology and finally discuss the results along with a brief performance analysis for optimizing real-world circuits. Starting with a bit of background, physical design is the process of converting a logical circuit description into a physical representation that can be manufactured. In PCB design, the schematic, like the example shown on the left, is the logical representation. The corresponding physical layout is displayed on the right and consists of the component footprints laid out on the board region in a way that they can be wired together. The top figure is an illustration of the placed circuit, and at the bottom is the result after routing the components. From a functionality perspective, the schematic and the layout should be identical. The logical representation can take the form of a netlist, which in our case is mathematically described using a hypergraph. The nodes of the hypergraph represent component pins, while the hyperedges represent nets. Now, the placement task typically takes the form of an optimization process that maximizes or minimizes a cost function. A common goal is to minimize the overlap-free wire length, such as half-perimeter wire length, since this directly correlates with performance, power, and area objectives. Moving on to existing literature, we have found that research in PCB physical design is sparse and can be divided into two classes. The first category focuses on automating component placement on the PCB, primarily to reduce wire length. The second, which is more prevalent, includes methods that not only aim to reduce the overlap-free and wire length optimized placements, but also take into account performance criteria. Examples include optimizing placement to reduce thermal hotspots and minimizing energy losses due to parasitic elements in power delivery systems. Meta-heuristic optimization methods, such as genetic algorithm, swarm optimization, and simulated annealing, are very common in this regard, since circuits tend to be small and often in the region of hundreds to thousands of components. By contrast, research in integrated circuit design is by far more active and driven by both academia and industry. The reason for this is that taping out integrated circuits with billions of transistors is highly reliant on the quality of the automation tools used to design them. The state-of-the-art techniques in this domain employ analytic placement methods, where a differentiable objective function is defined and minimized using numerical techniques. The main advantage these methods have over meta-heuristics is that they can scale to large problem sizes. In recent works, we have also seen machine learning being employed in tasks like floor planning, both in a hybrid manner with existing methods and in end-to-end workflows. So, what is the motivation behind this work? Meta-heuristics can be justified for PCB placement since the problem sizes are small and given sufficient time, they tend to quantitatively demonstrate good results. However, when we analyze the results generated by a proven meta-heuristic algorithm such as simulated annealing on small circuits, we could obviously see room for improvement. So the question we try to answer is, can we use machine learning to understand how to place components in a smart way and use that experience over and over again? That is by contrast to making random decisions hoping to get lucky over time. To achieve this, we decided to use reinforcement learning since it is a suitable tool for combinatorial optimization, and additionally, we have no restrictions on the cost function. That is, we can define it in any combination of metrics that work best for us. So in our methodology, we take a bit of an unconventional approach towards solving the problem, which is inspired by topics in complexity theory. We treat every component on the PCB as an autonomous agent that operates under some set of rules. These rules are what we learn using reinforcement learning, and in the simplest scenario, We expect the agent's actions, which are a manifestation of these rules, to demonstrate state updates that minimize overlap-free wire length in the long term. The final solution then emerges as a result of all the components interacting together under this set of basic rules. The realization of this methodology in a general manner from a small set of training circuits is what we will describe in the remainder of this presentation. So the first step is to automate the placement problem is to formulate it as a Markov decision process. And here we need to define the observation space, the action space, and the reward function. Here it is important to keep in mind that the agent represents a single component. So starting with the observation space, it contains perception information for understanding the immediate vicinity surrounding the current component, as well as directional information that guides movement towards regions that reduce wire length. So the perception information is captured using a set of masks derived from a circle centered around the current component. Half of the features contain information related to overlap, while the remainder describe non-overlapping objects that fall within the circle's area. The direction information is derived in the form of r-theta vectors computed directly from the netlist. One vector is simply the linear combination of all nets and points to the general direction that will reduce wire length. Another is computed between the current component and connected neighbors. Also included in the observation space but not shown in this slide are the components on position and orientation. The action space defines the output of the policy and how that will correspond to the movement of the component on the printed circuit board. We chose a continuous action space containing three outputs between 0 and 1 to encode an r-theta vector for translating the component on the board. The orientation is captured by the third output, which is interpreted discretely such that orientation can legally accept values that are integer multiples of 90 degrees. The advantage of a continuous action space over a discrete one is that it offers more granularity at the cost of increased training effort. Now, looking at the reward function, its purpose is to evaluate the quality of an action, and at a first glance, it simply consists of the linear combination of two wire length terms and overlap. The tangent function is used to aggressively follow actions that increase task performance, and the factor of pi divided by 2.1 clamps the reward value for practical reasons. The term zeta is also introduced for practical purposes and comes into effect if the component is moved outside the board region. The more subtle aspects of the reward function include the wire length normalization. We normalize with respect to the initial conditions. These are terms with a zero subscript, which promotes actions that lead to wire length reduction relative to the start of the episode. However, this is not enough, since different nets have different characteristics. Normalizing with respect to the best historically known wire length for a particular net, these are terms with an E subscript, decouples the reward from any particular net instance, and thus ensures consistent feedback across different circuit topologies. Moving on to the experimental setup, we use a dataset of 9 small circuits, 6 exclusively for training and the remainder for evaluation. While this may look small, every component in the circuit netlist contributes training data. The training process is illustrated by the flowchart on the right and starts by randomly sampling a layout from the training set and initializing all components on the PCB layout region. Then, for every episode step, the policy is invoked on all the movable components in the netlist, every time sampling an updated view of the state and taking an action to influence it. Since every component has a different set of neighboring components and different connectivity patterns to these neighbors, this leads to a high sample diversity, which aids in learning robust and general behaviors. In terms of learning algorithms, we use off-policy advanced actor-critic methods. Looking at the experiments, we conducted two sets of experiments. The first four configurations in the table on the right consider all elements in the reward signal, each emphasizing a particular term. The corresponding average return charts for these configurations are shown on the left of the slide. The remaining 6 configurations, 5 through 10, are ablation experiments, where we either eliminate the Euclidean wire length by setting n equals to 0, or the half-parameter wire length by setting m equals to 0. As illustrated in the charts, the training process has two key phases: a sharp increase from the training starting point to around 75,000 steps, and from there a slower increase until plateauing to some value. What's happening here is that in the first phase, the agent learns to operate within the board region, and in the second phase, it's learning behaviors for solving the task. In terms of reinforcement learning performance, soft-actor critic in general demonstrates lower variance across multiple training runs. And additionally, as shown in green, it offers significantly higher average return when half-parameter wire length is emphasized in the objective function. TD3, on the other hand, shows a slight advantage for Euclidean wire length or overlap when these are emphasized. These are respectively highlighted in green and orange. Having looked at the performance from the machine learning perspective, now it's time to evaluate the best policies on unseen circuits and measure their performance alongside a simulated annealing baseline in terms of the post-routing wire length. So the process starts by generating a random layout that is separately optimized by both the baseline algorithm and our best policies. Afterwards, the optimized layouts are routed using NA star algorithm, and we perform this process up to 4 times and average the results. In general, what we find across all our experiments is that policies that optimize for wire length, that is, a high value is assigned to the n and m coefficients, obtain the best results, and the largest margin over simulated annealing regardless of the learning algorithm. Using more conservative policies that equally balance wire length and overlap, we are able to measure the performance of simulated annealing, and the main benefit here is that the likelihood of yielding an overlap-free layout increases significantly. For configurations that solely emphasize overlap, by assigning a high weight to the p coefficient, tend to not yield good results, since the policy's incentive is then to resolve overlap arising from the random initialization. Finally, it is interesting to show some key optimization steps that demonstrate the learned placement behaviors. In this example, we show that the component self-organizes around the anchor IC in a matter of 30 steps, as they move from a random placement in figure A to something that resembles the final layout in figure C. This circuit is interesting because it involves 4 components, 4 component clusters that are tied together on one end and separately on the other. In this case, our methodology yields very good results, while simulated annealing in general has performed poorly, since it is split between optimizing the wire length for one cluster at the expense of the other. Therefore, experience seems to play an important role for optimizing circuit placements quickly and effectively. We encourage you to visit our open source code repository for more demonstrations. This brings us to the end of this presentation, and as a quick recap of our contributions, we have formulated the placement problem as an MDP and demonstrated 21% wire length improvement over an open implementation of simulated annealing. We have additionally demonstrated our policies in action, showing that the learned techniques are robust. And finally, all our source code, raw data, and setup scripts are publicly available to facilitate reproducibility of this work. We would like to thank you for your attention, while we look forward to discussing with you further at the DATE conference in Valencia.